Alright, so let us next start the fifth chapter on complex numbers and quadratic equations. We will do mathematical induction afterwards. Our discussion starts with this quadratic equation. X square plus 1 equals 0, which has no real number solution. There is no real number x that satisfies this equation, and the reason is that the square of any real number is non-negative. It's greater than or equal to 0. And this we know from properties of real numbers. The only real number whose square is equal to 0 is 0 itself. And the square of any non-zero real number is positive. For example, 2 square is positive, and also minus 1 square is positive. So if this cannot be negative, how can it be minus 1? That is why this equation has no solution in the system of real numbers. But say we want a number system in which this equation has a solution. So that is the system of complex numbers. What we do here is we are going to assume a solution to this equation in the beginning itself. And we even give it a name. We call it I. Let I. So having a solution to this system means having square root of minus 1, because if you just simply, without regarding the rules of real numbers, just go for solving this equation, what will you get? You subtract 1 from both sides, you get x squared equal to minus 1, and then you take square root. So you get this quantity. But that quantity does not exist in R. So we are assuming its existence outside R. This means that I is not a real number. B a quantity such that I square is equal to minus 1. Okay, so that's what I does. Whenever you take its square, it becomes minus 1. And we actually give it a name also. We call I the imaginary unit. Although in most of the treatments of real number system, this is what the imaginary unit is called, means it's named, that is I. But in electrical engineering, I denotes current. So they use the letter J to denote this same thing. Okay, we will however use I. And now with the help of this quantity, we are going to define a complex number. A complex number is a number of the form a plus I b, where a and b are real numbers. Okay, so that's what complex numbers are. They are quantities which look like this, a plus ib, where I is that assumed quantity, our imaginary unit, and a and b are real numbers. And we denote the set of complex numbers by the letter C, just like R denotes the set of real numbers. By C. You may find it a little difficult to write this type of things, this font. It's called blackboard bold font. What happens is that when you write on a blackboard using your chalk piece, if you hold the chalk like this and then write R, it looks like this. Similarly, if you hold your chalk piece like this horizontally and then draw C, it looks like this. You just simply write capital R and C. That's it. So C denotes the set of all complex numbers. Now the first thing we are going to do in this set is we are going to define a rule that will tell us which complex numbers are really the same number and which are different. In other words, we are going to define what equality of complex numbers means. For any two complex numbers. Although the complex numbers look like this, but you can of course give them a single letter name, say Z or W. So for any two such numbers, say C plus ID in C, we define them to be equal if A is equal to C and B is equal to D. That is, if the first two real numbers, lacking a better name at this stage, I am calling for the complex number A plus IB, I am calling A the first real number and B the second real number. We are going to give them some names, okay, it's coming. So two complex numbers are equal and we define them to be equal if their first parts are identical and second parts are identical. So once this has been established, so now we just know that two complex numbers are equal if they are identical looking. If you have 1 here and you have 2 here, say 1 plus I2, that cannot be equal to 1 plus I3 because 2 is not equal to 3. The other complex number also has to be 1 plus I2, then only these two will be equal. And with this idea, we next define this. Given this in C, we call A the real part of Z and denote it by REZ. Okay, so that number which I was calling the first number, that is called the real part of the complex number set, and we denote it by rez, and we call B the imaginary part of Z and denote it by writing imZ. Why did I not define these real and imaginary parts before defining equality? It is because now each complex number has exactly one real part and exactly one imaginary part. Before defining equality, that was not necessarily the case. I mean, without any notion of equality, we did not really have any way of telling whether this is not true. If it were true, it is not true now that we have this notion of equality. If it were true, then real part won't really be unique, because in that case real part would be 1 as well as 3. That's not the case now. It seems like a non-issue, but in fact there are number systems where components of a number are not unique. Let me give you one example. You are well familiar with the rational number system. In the rational number system, how do rational numbers look? They are ratios of integers. Consider the rational number which has this representation in the decimal system, 0.5. Now you can also write this rational number as 1 over 2, 1 divided by 2. And at the same time, you can also write it as 4 divided by 8 or minus 1 divided by minus 2. In fact, there are infinitely many ways in which you can write this rational number as a ratio of two integers. So, unlike the real and imaginary parts of a complex number, we cannot say the numerator and the denominator of a rational number. No, they are not unique. That is why we need this notion of equality. These rational numbers are equal because by definition they are equal, because 1 times 8 is equal to 4 times 2. The definition of two rational numbers say that when that happens, then they are equal. But that does not make their component parts equal. So it's not like this equality of complex numbers. Now examples of complex numbers, of course, are easy. The book gives us some examples, and you can also think of some examples yourself. Say this is a complex number, 2 plus I3 or minus 1 plus I square root of 3, or anything you can take actually. Say 4 plus I minus 1 over 11. These examples I think have been chosen just to show that the real and imaginary parts can be any real number. They can be rational number or integer or even irrational number. They just needs to be real numbers. Okay. Now, let's consider this example. Find real numbers x and y such that 4x plus I times 3x minus y equals 3 plus I times minus 6. So what will you do? Because it's given that x and y are real numbers, obviously 4x and 3x minus y are also real numbers. That means this expression on the left hand side of this equation is a complex number. And the right hand side, of course, is also a complex number. Here the numbers are known, 3 and minus 6. So by the definition of equality, if this has to happen, then the real parts have to be equal. The real part of this complex number is 4x and the real part of this one is 3. They have to be equal and the imaginary parts also have to be equal. So we also must have this. From this we are getting that x should be 3 over 4. And from this, if you transfer this minus 6 to this side and you also use the value of x, you get this. That is what should be your y. Y should be 33 divided by 4. So using the definition of equality, you can know what x and y are. Okay. Now it's not enough to simply have a set of numbers and a notion of equality in that set. We also need algebraic operations on the set. Just like you have addition and multiplication of real numbers, we are now going to define similar operations for complex numbers. So let us first see addition, and this part is named algebra of complex numbers. For two complex numbers we define their sum by this formula: a plus c plus I b plus d. Addition is very straightforward. You add the real parts of the complex numbers separately and you add the imaginary parts of the complex numbers separately, and that they give you your sum. Oh, and okay, in this regard, before we see what properties this addition has, let me also make one thing very clear. This is something that people often get confused about. Both the real and imaginary parts of a complex number are real numbers. This is the real part of Z1 and B is the imaginary part of Z1. IB is not the imaginary part, only B is the imaginary part. Okay, so that is one place where people make mistakes. I also used to make mistakes when I was introduced to these things for the first time. Only B is the imaginary part. For example, here I root 3 is not the imaginary part, root 3 is the imaginary part. Okay. Now, this sum has some properties which are exactly like ordinary addition of real numbers. There in fact is, you can consider example, it will be very easy. You just take two complex numbers, say -1 plus I3, and you also take say 2 plus I times minus 3. Their sum can be obtained by adding the real parts. So you add minus 1 and 2, that gives you 1, and you also add the imaginary parts. Imaginary parts, okay, you add 3 and minus 3. Those are the imaginary parts, no I. So they give you 0. And you need to write I0. Do not simply write 1. Okay, this is just a rule that you should follow. It just shows that your result of the sum of these two complex numbers is also a complex number. Next we come to the properties. So the first property is very easy. It has a name also. Closure property. What it says is that for any two complex numbers like that one, their sum is again a complex number. It is called closure property because in a sense it is closed. It is closed means the set of complex numbers is closed under the addition of complex numbers operation. By performing this operation on two complex numbers, we again get a complex numbers. So we get trapped within the set itself. The operation does not let us go outside the set. In that sense, we are closed within the set. So that is why it's called closure property. The exact similar property the system of real numbers also has with respect to addition. If you take the sum of two real numbers, you again get a real number. You do not get anything outside the system of real numbers. Number 2. Commutativity. For any two complex numbers. Oh, and by the way, is it true? Yes, it is true. Why? Because you can see here, if A and C are real numbers, then their sum is also a real number. Similarly, B plus D is also a real number. So, this is really a complex number. It is not anything else. Next, commutativity for any two such complex numbers, not necessarily distinct. Okay, whenever we write for any or simply for, it means that we include the possibility that Z1 may be equal to Z2. The order in which you take the sum does not matter. Whether it's Z1 plus Z2 or Z2 plus Z1, you get the same result, which of course you can verify. In place of Z1 plus Z2, if you calculate Z2 plus Z1, what will you get here? C plus A and D plus B. But addition of real numbers is commutative. We know that for two real numbers A and C, A plus C is equal to C plus A. Similarly, B plus D is equal to D plus B. So that way, the commutative property for addition of real numbers causes the addition of complex numbers to also be commutative. Number 3. Associativity. If you have any three complex numbers again not necessarily distinct. It does not matter how you calculate this sum, whether you first add Z1 and Z2 and to that you add Z3, or you add Z1 to the sum of Z2 and Z3, you get the same complex number. That also, this also you can verify if you want. So this is called associativity, and the same property is true for real numbers and addition of real numbers. Next, existence of additive identity. Recall that the real number system has that special number 0, that if you add to any real number, you get back that real number. 0 has no effect on any real number with respect to addition. A similar number is present in this system also. For any, or maybe I should write like this. We have the complex number 0 plus I0, and we are giving this complex number the name 0 itself, okay, such that adding this complex number to the complex number set gives us set back. Just like adding ordinary real number 0 to any real number gives that real number back. Such an element is called additive identity. In the system of real numbers, the ordinary real number 0 is an additive identity. In this system, this complex number is an additive identity. An identity has no effect on the operation. And then there is another one. Existence of additive inverses. For any complex number, we have another complex number which we are calling minus z. It's a name given to this number, okay, and it is minus a plus I minus b, which again is a complex number, such that if I add this minus z to z, then I get the additive identity of this system. Just like every real number has its additive inverse, I mean it's negative. For example, 2 has its negative minus 2, so that if you add them up, you get the additive identity of the real number system, that is the real number 0. Similarly here also, and this number minus z is called an additive inverse of z. Okay, so that's why we say existence of additive inverses. Every element has an additive inverse. So you see, because the properties of this new operation that we defined today, addition of complex numbers, because the properties are exactly like those of the addition of real numbers. That is why we have decided to call this new operation addition. Okay, that is one reason. Otherwise, you can just call it something else also. You can simply call it an operation. But because it is just like the operation of addition of real numbers, that's why it is reasonable to call this one also addition of complex numbers. Now, with the help of this addition and these negatives of complex numbers, which are called additive inverses, we can define subtraction of two complex numbers. For complex numbers z1 and z2, we define z1 minus z2 to be this. z2 has an additive inverse minus z2. So, if you add z1 and minus z2, that we are calling z1 minus z2. That is the meaning of z1 minus z2. And it is subtraction of complex numbers. Similarly, subtraction of real numbers are also defined in terms of addition of real numbers and additive inverses of real numbers. You can take this simple example. Say you consider this complex number 2 plus I minus 6, or say minus, actually you can take anything, but I want to take the example that the book has shown, and from this you can subtract this complex number. So what do you then do? You first have to write the additive inverse of 6 plus I3. And what is that? You just have to change the signs of the real and imaginary parts of your original complex number. Here the original complex number is 6 plus I3. So changing the signs of the real and imaginary parts, you will get minus 6 and minus 3. And then by the above definition, so this is minus of this. By the above definition, you then have to add these two things by our definition of addition, which tells us to add real parts. So 2 minus 6 is minus 4, and add imaginary parts minus 1 and minus 3, which is also minus 4. Okay, similarly, you calculate this one. This I am leaving to you. You carefully first write the additive inverse of 2 plus I minus 1, and then to that you add 6 plus I3. Your result will be the subtraction. Alright. And next, we also have to define multiplication. And this is a little not so straightforward, not as straightforward as the definition of addition. For z1 equal to a plus ib and z2 equal to c plus id, we define their product Z1, Z2 by this rule AC minus BD plus I times AD plus BC. Now let us also, at once the rule looks complicated, okay, but let us see what rule we are following to write this number. So let me write the numbers in their full forms again here below. How is the real part of this product coming? For the real part, what you do, you multiply the real parts A and C. Okay, so you get AC. You multiply the imaginary parts also, B and D. You get BD and you take their difference. First component times first component minus second component times second component. What happens to the imaginary part? For the imaginary part, you multiply the farthest components. That is A on this side and D on that side. Or in other words, you multiply the real part of your first number and the imaginary part of the second number. And then, so that gives you AD. And then you multiply the nearest components, B and C. So that means the imaginary part of the first number and real part of the second number. Okay, if you try to remember in terms of real and imaginary parts, you will get confused. So you instead think like this. For the first component, first, second, and then there is minus. For the second component, you have plus and farthest components, nearest components, BC. Okay, so that's how you can remember this product. But again, no matter how many different elaborate rules you make to remember this type of things, unless you do practice, you will definitely forget. Okay, so this is our product, which looks quite complicated, but let us at least note one thing here itself right now, that just like the sum of two complex numbers is again a complex number, the product of two complex numbers is also a complex number. Why? Well, A, B, C and D are real numbers. So AC minus BD is also a real number and AD plus BC is also a real number. That means this is a complex number. And that is why we have the closure property for complex multiplication also. For Z1 and Z2 in C, their product is again in C. So just like addition, multiplication also does not let us go outside the system. And this corresponds to multiplication of real numbers. When you multiply two real numbers, you again get a real number, just like that. Number 2, the commutative law is also true. See, things were so straightforward, about these laws when the operation was addition, but multiplication is comparatively more complicated, so it's not really that obvious. You have to really see that Z1, Z2 is equal to Z2, Z1. You try these proofs. Okay, all you have to do is to just calculate these two products and see that they are equal. It's a little surprising to see that in spite of having such a comparatively more complicated definition, the laws continue to be true. Exactly similar laws continue to be true. In fact, we also have associativity for any three complex numbers we have this. Proving this will be the most complicated, I think, because the expressions will be quite long. Z1, Z2 will look like this, and then you have to multiply Z3 with that. But here also, it turns out that they are equal. Just like ordinary multiplication of real numbers is associative. Next, here also we have an identity element. But this time, multiplicative identity. For the complex number 1 plus I0, which we are calling just 1, we have Z1, where this one has this meaning 1 is equal to Z for any complex number Z. I need a little ink. This also you can verify. You can verify means, let me verify this now for you. At least let me show you that this is true. So, what shall we need for this? Say, this is A plus IB. So that means Z1 will be equal to A plus IB times 1 plus I0. So recall the rule, A first component times first component minus second component times second component. A times 1, let me write first, A1 minus B0 plus I, farthest components plus nearest components. A times 0 plus B times 1. So what are you getting? A plus IB. So that is again Z. Okay, so just like the real number 1, which is the multiplicative identity in that system, this complex number is the multiplicative identity in this system. So in this regard, complex multiplication shares these properties with real multiplication. And in fact, there's more. Inverses also exist except for one number, which is 0. So just like you have, say you have a real number x, but with the condition that x is not equal to 0, you know that there exists a number which if you multiply with x, you will get the multiplicative identity 1, and that number is of course your reciprocal of x. In the system of real numbers, this is what happens, and a similar thing happens in our system of complex numbers. Let z equal to a plus ib be not equal to 0. What is that 0? That 0 is the complex 0, 0 plus I0. Be in C. What does this mean? This a plus ib not being equal to 0 plus I0 means that either a is not equal to 0 or b is not equal to 0 or both. Both cannot be simultaneously 0 because otherwise this will be equal to 0. So a square plus b square is not equal to 0. If a and b are two real numbers which are not both 0, obviously the sum of their squares cannot be equal to 0. Why? Because for this to be 0, both a and b have to be 0, and that comes from the non-negativity of a square and b square. Because they are both non-negative, they cannot cancel each other. If the sum has to be 0, they have to separately be 0 both. So now our a square plus b square is not 0. Hence, this is a legitimate complex number. A divided by a square plus b square plus I minus b divided by a square plus b square. You can divide a by this non-zero real number. So this is a real number, this is another real number. And we give this complex number a name also, Z inverse. Such that, let me not end the sentence here itself. Z inverse is equal to 1, and this 1 is the complex multiplicative identity 1 plus I0. I want you to verify this. Okay, so you actually multiply this one and this one, you have to see that you really get 1 plus I0. You will get. Okay, I just want you to see that for yourself. So far, all the properties that we have said or we have demonstrated that the complex multiplication has exactly similar properties we also have for real multiplication, and that is why this is, it makes sense to call this new operation multiplication. And there is one more final property, distributive laws or distributivity. These laws connect addition and multiplication. All the properties that we have so far discussed, either they were only about addition or only about multiplication, but now we are going to have both of them. Z1 times Z2 plus Z3. So you have both multiplication and addition. This equals Z1 Z2 plus Z1 Z3. Again, you have to verify this and see that it's really true. also if you change the order, still it's true. We call these things distributive laws. Specifically, this is called the left distributive law because multiplication distributes itself over addition from the left side, and this is called the right distributive law because multiplication distributes itself over addition from the right side. Okay, so with all these things, we now have our complex number system. You may be wondering about that I. In the beginning, we just simply declared as if blindly that I is a quantity whose square is equal to -1. And then we just went on and said that symbols which are like a plus ib, they are called complex numbers where this and this happen. But did we see I square being -1 anywhere? No. So what is going on? And what purpose does this I serve in this symbol? Other than simply being a way of identifying what the imaginary part is. Is that the only purpose that I serves? Well, in a sense, yes, but at the same time, we are now going to see why I square really has been considered to be -1. You see, we have agreed to call this complex number 1. In a sense, this is not true because this is not exactly a real number. It really has two parts. The first part is 1 and the second part is 0. Having a 0 part does not really make an object not have that part. Let me give you one example. You have done coordinate geometry in lower standards. There you have come across Cartesian coordinates of points in the plane. For example, if I give you this point 1, -2, you know how to locate it on your graph paper. Now, if I give you instead this point 1, 0, which you know lies on the x-axis, simply because the second part of this composite object is 0, do you simply write 1 in place of this? No, you never write 1 because you know that this is an ordered pair of real numbers, whereas this is a single real number. In that same sense, are we really justified in writing 1 here? In a sense, we are. But the problem is that at this stage, I won't really be able to fully explain. I mean, I can explain, but it will go over your head. This is not the right time. This is the first time we have been introduced to complex numbers. So right now, many things, many issues will be pushed under the rug. You have to first of all gain familiarity with these numbers by handling them. Once you gain enough experience and familiarity, then only those issues will again be taken up one by one, not now, and then they will be answered. So let us now see how I square is -1. Just like we have decided to call this number 1 for some reason, there is a justification. This one is the complex multiplicative identity, just like our ordinary real number 1 is the real multiplicative identity. So it's not a problem to call it 1 if we have the idea that it's not the real number 1, but we actually are using this one as if it's the real number 1. That is the issue. So that cannot be answered right now. Instead, let us do something similar. You consider this complex number 0 plus I1. Let us agree for now to call it I. Okay? And with this new meaning of I, see, initially we did not really know what I is. We just simply told that there is a quantity I whose square is minus 1. Now we are calling this complex number I. Let us now take its square. And let us apply the definition of complex multiplication. We already have that. So first times first minus second times second plus I farthest components 0 times 1 plus nearest components 1 times 0. So what are you getting? Minus 1 plus I 0. Just like you have decided to call this 1, in that same sense, can you not call this minus 1? In fact, from another point of view, it really is minus 1. What is the additive inverse of this complex number? Minus 1 plus I minus 0. So in that sense, because you have decided to call this 1, so it really is minus 1, minus of this. So you are really getting now I square equal to minus 1. It seems like magic and a little sketchy. Admittedly so, because many things cannot be answered right now itself. And before I end the video, let me just raise two such issues which cannot be answered right now. How did we start our discussion? We simply called the symbol a plus ib a complex number. At that time, did we really have any meaning assigned to this plus? Or for example, this product of I and B? No. Why? Because you see, let us first concentrate on the product IB. We know how to multiply two real numbers. B is a real number, but I is not a real number. So what is the meaning of IB? If you say that IB means the product of the complex numbers I and B, that also runs into problem. Why? Because when making this definition, multiplication of complex numbers was still not there. So IB really has no separate meaning. Similarly, we don't really know what IB is, and still we are adding that to A. So obviously this plus also has no meaning. But then why are we writing plus? Why are we writing multiplication? These questions will be answered later. Okay. There is no problem with these things. The only thing is that you have to start the construction of complex numbers more seriously. I would just simply say that much. So there are other things also that come after this. For example, absolute value of a complex number, and then we will see what the other things are that are there. So that's just it for tonight. See you tomorrow, and I believe tomorrow we have what? Commutative algebra again. I think so. Okay, so see you tomorrow with that. Until then, this is me, Lucifer from a mathematical room. Have a nice night.